This is part 2 of chapter 11 homework for Physics 102A. So starting with number 25, we have a fundamental frequency of 220 Hertz. For a closed tube, remember that the overtones are every odd multiple of that frequency. So the third frequency, that would be the first overtone, is 3 times the fundamental. The next one is the fifth frequency, which is 5 times the fundamental, and so on. So the first overtone, which is, we call that F sub 3, that's 3 times the fundamental frequency. That's 3 times 220 Hertz, and that gives an answer of D, 660 Hertz. The next one, number 47, is the submarine. First, it's good to draw a picture of this. So you see that the submarine is 65 meters below the surface of the water. It lets out a sonar pulse down to the bottom of the ocean and then back up. So the first thing we need to figure out is how deep is it from the submarine to the bottom of the ocean. So we start with distance equals velocity times time. Now, the distance that the sonar pulse is going to travel is twice x, twice the depth from the submarine to the bottom of the ocean. So for distance, we'll call that 2x equals vt. Solving for x, we then have x equals 1/2 v times t, and then we plug in the numbers. X equals 1/2. We need the speed of sound in water, which is, you can look that up in the book in chapter 11, but it's 1480 meters per second, times the time it took for the sonar pulse to go, so 0.86 seconds. What we get is a distance of 636.4 meters from the submarine to the bottom of the ocean. The question is asking, how deep is the ocean? So we have to add to it the 65 meters that the submarine is under the water. So when we add 65 to 636, we get 701.4 meters. And there were only 2 significant figures in this problem, so it's proper to round the answer off to 700 meters. The next problem is number 49. We take the speed of sound to be 343 meters per second at 20 degrees Celsius. That's something that was given in class. But also, we can get it from this equation, that near room temperature, velocity is 331 plus 0.6 times the temperature. So when you make that temperature 20 degrees Celsius, you get a velocity of 343 meters per second. From there we can find distance, because distance, x, equals v times t. So 343 meters per second times 35 seconds is 12,005 meters. With significant digits, it'd be appropriate to say 12 kilometers, but we're going to need that exact number, 12,005 meters, for part B. Part B is asking, what if the speed of sound changes? What would the new travel time be? Meaning, we're set with, it's going to be the same distance, 12,005 meters, but what would the new time be? So this takes into account the new velocity. You can get this velocity, the speed of sound, at 0 degrees Celsius from this equation, 331 plus 0. So we plug in 331 meters per second into this equation, and then we get the travel time of 36.27 seconds. When the speed of sound was faster in part A, it only took 35 seconds, but now that the speed has gone down just a little bit due to air temperature, we have a slightly longer travel time. The last problem on this video, number 67. We have a closed tube, which is the kind we talked about in class. This is the sort of diagram I drew in class, and what we see is the length of the tube is equal to 1/4 of the wavelength. We start with our basic relationship between wavelength, speed, and frequency, v equals lambda f. We want to find lambda, so we do lambda equals v over f. Putting these two equations together, the fact that lambda is v over f and length is 1/4 of lambda, we can then say that length is v over 4f. Now, we plug in those numbers to solve for the length. So for part A, the length is going to be, and again I'm using this equation right here, the speed of sound, we're going to take that to be 343 meters per second, divided by 4 times the frequency given in part A, which is 56 hertz. What we get is the length of the tube of 1.53 meters. For part B, we use the same formula, but we plug in the new frequency, 262 hertz. Gives us a length of 0.327 meters. Notice that the higher pitch is given by a much shorter tube, and that goes with our intuition that a piccolo, which produces very high sounds, is a very short tube, whereas a bassoon, which produces deep sounds, is a very long tube. So the higher frequency is produced by an organ pipe with a much shorter tube. Parts C and D, you can see the answers in the back of the textbook, but they're done the same way, just by plugging in whichever frequency is appropriate.